Presenting a component of research which is part of an ARC linkage project between the university and Aluka, or the industry partner Aluka Resources, and more recently Kate Holland has joined us from CSIRO Land and Water. The partnership aims to complement Aluka's on-site rehabilitation program and their mine sites in the far west of South Australia, and we aim to improve our understanding of plant growth in arid and saline environments. And this is, we're hoping to use to inform them, to assist their rehab managers to, in their efforts to comply with licence conditions that require them to restore ecosystem function in post-mine areas. So Aluka have been mining at the Jacinth Ambrosia mine site since 2009. And it's a heavy mineral sand mines, and they're primarily extracting zircon, titanium and rutile. It's an open pit mine, which can be as deep as 40 metres, and saline water from a nullarbor paleo channel is used, was transferred on site for on-site processing plant. The process produces a tailings which is hypersaline. The mining agreement between the government and Aluka, or the PEPA, have fairly strict rehabilitation conditions, including a commitment to restore pre-existing soil profile and function, and also to restore ecosystem and landscape function that reflects the pre-mining ecosystem. So the mine's located in the far west of South Australia in Yellabinna Regional Reserve. It's the first mine that was allowed in a regional reserve, and the area is relatively undisturbed, and there's no recent grazing activity. It's an arid part of the state with low annual rainfall, and rains are generally reliable during winter, but we also get summer heavy downpours in La Nina years that creates flooding during summer. The plant community mostly impacted by the mining is sparse open woodland dominated by western myall or Acacia paracarpa, and this has interspersed myall and mallee creek lines and sandy rises. The understory community is dominated by chenopod shrubs and a suite of annual herbs that come through with suitable conditions, suitable rainfall and temperatures. Western myall trees are long-lived acacias. They can live in excess of 250 years, and the tree is considered a keystone species in this region because of its ability to modify establishment conditions that influence plant communities beneath its canopies. So just to give you an idea of the undisturbed soil profile before mining, the topsoil contains the natural soil seed bank, which is the top 3 centimetres of the soil. Brown sandy loam occurs down to about 3 metres deep, and this often overlies a very thin layer of calcrete, up to 1/2 metre. Below this, red sandy loam extends down to about 15 metres, beneath which is what's referred to as Aldeia sands. The mining process involves clearing and stockpiling the vegetation, and then stripping the different soil types and stockpiling these separately. Most of the mineral extraction is from the Aldeia sand, but they also obtain it from the sandy loams. So during mining, the pit void is backfilled with the tailings to a depth of around 6 metres, and then the overburden soils, which are the sandy loams and the topsoil and subsoils, are returned. And rehabilitation is solely reliant on natural seedling emergence from the soil seed bank, and this is also dependent on receiving follow-up conditions like suitable temperatures and rainfall. So western myall roots have very extensive root systems. Our root mapping work at Jacinth Ambrosia shows that lateral roots extend more than 20 metres away from the trunk, and that some of these have vertical sinker roots coming from them. Tap roots and sinker roots have been found at really extreme depths in the mine pit, around 27 metres. So this discrepancy between the natural rooting depth for the western myall and the shallow overburden soils that are being returned over tailings in the rehab areas raises questions about how altered plant soil water relations are going to affect tree survival in the long term. So we wanted to examine the transfer of water between myall roots and soils to understand how they manage to support such large root networks. which has direct implications for rehabbing. Our research aims was to examine water redistribution by Western Myall following heavy rainfall, which is commonly referred to as hydraulic redistribution. So hydraulic redistribution is the redistribution of water between soils and roots. It is a passive movement in response to gradients in water potential. Water moves from wetter soil horizons to drier soil horizons, so from soils with a higher water potential to those with a lower water potential. Originally we thought that it was movement in one direction, so from deeper drier soils, wetter soils up to surface dry soils. But now we know that the movement can be in all sorts of directions, both vertical or downwards, upwards and laterally. So this diagram illustrates how important it is to plant survival. So after rain, water is transferred downwards into deeper soil horizons where it can be used to grow and sustain root systems, or it can be stored in the soil. When surface soils become drier, this water is then transferred towards the surface to sustain surface roots, and or will be used for transpiration. So for our study, we chose 2 Western Myalls that were representative of growth form and age for this particular area. We used an air spade to expose the root network at the base of the trunk and installed a series of instruments that measure sap flow in the xylem or the sapwood. We targeted the taproot and vertical roots because we wanted to capture downward movement in the tree. And when I refer to a lateral root, I'm just describing a root that we detected no sinker or vertical coming off it before it had disappeared into the soil and was lost to view. So sap flow meters measure sap flow direction, velocity and volume can be obtained from the measurements using the heat ratio method. So 3 needles are inserted into the sapwood of the stem or the root, and the upstream probe and downstream probe have temperature sensors that detect heat pulses that are produced by that centre needle, and the changes in the ratio of heat can indicate sap flow direction and sap flow velocity. And the image on the right shows the placement of the sap flow meters on one of our trees, including 4 positions on the trunk. So I need to show you a typical sap flow pattern for a Western Myall. So it shows consecutive 24-hour periods measured in centimetres per hour and peaks around daytime. So each day sort of peaks here when transpiration is highest, and then slowly returns to around 0 at night time when transpiration no longer occurs. So sap flow velocity can be positive or negative, with positive indicating water movement towards the trunk and towards the canopy, and negative values indicate water movement downwards and away from the trunk and into the root system. So other measurements we took, we installed stem psychrometers to measure stem water potential and a series of soil moisture probes at different depths just to measure moisture in the surface of the soil, and an on-site weather station provided us with rainfall and temperature. So in July 2013, 3 months after installing instruments on the first tree, we finally received some good rainfall at the site. The preceding 18 months were below average rainfall, and the surface soils were very dry. Rain commenced on the 11th of July and continued for around 12 days, with a total of 50 mil being received. Soil sensors show that the water penetrated the soils between 20 and 40 centimetres depth, and this rain occurred while we're setting up the second tree. So I'm presenting results from the first tree because I have before and after rainfall data. So the response to the rainfall was pretty much immediate, and this is reflected in the results from the change in water potential in the stem. So it's measured in megapascals, and the arrow indicates the start of the rainfall. And so it shows that there's an increased volume in the sapwood of the tree, and this infers changes in water potentials between soils and roots. And here is what we see from some of the sap flow meters. So this is the sap flow response from the taproot. The sap flow is negative, and indicates downwards movement away from the trunk and into deeper soils. The negative flow is sustained for around a 2-week period, both day and night, so with and without transpiration. And from a plant physiology perspective, this is quite significant because nocturnal water movement was always seen as fairly minimal. And in fact, in earlier research, it was believed that nocturnal sap flow should be equal to 0. So here are 2 other vertical routes, and with a similar sap flow pattern to the taproot. And here is evidence that Western myalls redistribute water down into deeper soil horizons. So I've just added 2 other positions to the graph with positive flow, which demonstrate other types of patterns that we observed. And these are primary lateral routes. And the final destination of water in these routes is unclear. It could have been transferred up the trunk for transpiration, or to be used for transpiration, or it could have been transferred into other laterals or vertical routes, even on the other side of the tree. So overall, the response to rainfall was rapid. It occurred within an hour of the rain commencing, and a strong response was measured in all the positions that we had sensors on. It was highly complex, with a positive and negative sap flow measured in various positions, including 3 positions on the trunk having positive flow and the other side of the trunk with negative flow. So as mentioned before, the response was prolonged for a 2-week period, and we can also say that process is not season dependent because we had these sensors on for 2 years and we measured similar responses to rainfall in different seasons, in 3 different seasons. And this makes sense considering the arid zone climate is so variable. We estimate that 20% of the tree's water budget was redistributed into deeper soil horizons over a 14-month period, and this shows how important it is. So we know that Western myalls have extensive and deep root networks which depend on the redistribution of water to grow and sustain them. And it's critical that the process is a critical process that enables the tree to survive extended dry periods and droughts. It is likely to occur in other tree species at the site, particularly the mallee, for which we've found roots at comparable depths to the myall in a mine pit. And an important consideration is that the redistribution of water towards the surface during dry periods may actually influence the distribution of understory plants. And this is because understory plants may benefit from this water movement to the surface during times of water stress. So our research has implications for restoring myall populations in rehabilitation sites. This is mainly due to the shallowness of the overburdened soils above tailings. Much of the rooting zone will need to be in the tailings, and these have very different chemical and physical properties to the undisturbed soils. For instance, tailings are hypersaline due to the groundwater used in on-site processing, which will change osmotic pressure in particular and heavily influence the ability of water to move between roots and soils. We also know that tailings have reduced water holding capacity in comparison with undisturbed soils, which will influence water storage in deep soil horizons. If the process becomes inhibited, we may expect myall roots to develop to a certain depth and for trees to reach a certain age, but they may not have the resilience to withstand long-term dry periods and droughts. It takes around 75 years for a Western myall to reach maturity or reproductive maturity, and so there's a real threat to re-establishing these trees in post-mine areas. And this leads us to think that Western myalls and other deep-rooted species may actually be excluded from the rehab plant community. So most importantly, this needs to be consideration from a regulatory point of view, especially when approving any future expansion of mining in the region. And I'd like to acknowledge my technical support and field assistance. Thank you.
Now, we don't have time for questions, so if you've got